You think you understand what empty means. The space between your fingers right now. The gap between Earth and the moon. Nothing there, right? Just nothing.
The elegance of this
Well,
theorem. It reveals
Richard
the
Feynman, one of the
fundamental
greatest
nature of
physicists of the
universe.
20th century, would tell you you're dead wrong.
Unbelievable.
The truth is stunning. Empty space doesn't exist. Where you see nothing, there's actually a churning chaos of energy particles flickering in and out of existence billions of times a second. Invisible forces weaving reality itself. Stick with me. I'm about to show you the experiment that proves it. Imagine you take two perfectly smooth metal plates and stick them in a vacuum chamber. Strip away every air molecule, every dust particle. Nothing left between them. Total emptiness, yeah? But then something wild happens. The plates start pulling toward each other. Something invisible is squeezing those plates together in the middle of nothing. Your intuition says this shouldn't happen, but it does. You can measure it. A real force coming straight from the vacuum. Let that sink in for a second. For centuries, people couldn't get a handle on vacuum. Ancient Greeks thought nature hated it, literally abhorred it. Aristotle was convinced truly empty space couldn't exist. Medieval philosophers spent centuries arguing whether God would even allow total nothingness to exist. Then Newton comes along. He describes space as this empty stage, right? Objects move across it. Gravity works through it. But the space itself, just nothing. A backdrop. An inert container where physics happens. Fast forward to the 1800s, physicists start getting nervous. Light travels through empty space, right? But how? They decide there must be something called luminiferous ether, an invisible substance filling everything. Except, experiments can't find it.
Pressure is building.
Michelson and Morley try to catch the ether wind in 1887. Nope, it's not there. Then Einstein crushes the whole idea with special relativity in 1905. Light doesn't need a medium. Back to square one. Space is actually empty, except it didn't. Not even close. Because right around the same time, quantum mechanics enters the stage, and it has completely different ideas about emptiness. Werner Heisenberg in 1927 figures out something wild. You can't know everything about a particle simultaneously. Want to pin down its position and momentum? Nope. Can't have both. The more precisely you know one, the foggier the other becomes. And this isn't because your instruments suck, it's built into reality itself. Nature is fundamentally uncertain, and that uncertainty doesn't stop at particles, it applies to something weirder, energy and time. The math is elegant. Delta E times delta T is greater than or equal to h bar over 2. In plain English, uncertainty and energy. Times uncertainty and time can never be smaller than half the reduced Planck constant. Translation? If you look at a system for an extremely short moment, the energy becomes fuzzy. It can wobble. It can actually borrow energy from nothing, from absolute zero, as long as it pays it back almost instantly. This doesn't break energy conservation because the loan happens too fast to catch. Now picture an empty space. In classical physics, the vacuum has zero energy, zero particles, zip. But quantum vacuum? That's where it gets crazy. Because of Heisenberg's uncertainty, those energy loans create something wild. Virtual particle pairs just pop into existence. An electron and a positron materialize from absolute nothing. They hang around for an absurdly tiny fraction of a second, maybe 10 or 23 seconds. Then they crash into each other and vanish, the energy returned to the void. Pause for a second. Let that sink in. The vacuum is absolutely boiling with this. Quarks popping up with their antiparticles, virtual photons, gluons, all of it churning in this quantum foam that fills every inch of space. You're probably thinking, okay, but this is just theory, right? Abstract math. How do we actually know this happens? Well, we can measure it. This is exactly what Hendrik Casimir realized in 1948. He's working at the Philips Research Labs in the Netherlands, thinking about van der Waals forces, and he has this insight. If you squeeze two uncharged metal plates really close together in a vacuum, the quantum fluctuations between them would actually be different from the fluctuations outside. Here's how it works. Virtual particles can emerge at any wavelength, long-wave photons, short-wave photons, all of them. But squeeze two plates close together, and only certain wavelengths fit between them. Long waves get blocked. Outside, all wavelengths can show up. Boom, you've got an imbalance. More quantum activity pushing from outside than inside. The plates get squeezed together, not by magnets, not by electricity, by the raw activity of the vacuum. Casimir did the math. The force is minuscule. For plates a micrometer apart, we're talking less than a millionth of a Newton per square meter. Tiny, but measurable. Fast forward to 1997. Steve Lamoureux at the University of Washington runs the actual experiment, sets up the plates, blocks out every external vibration, measures the force. You know what? It was there. Exactly as predicted. You can measure the force of nothing. Think about that. So virtual particles aren't just mathematical games, they're real. They shift energy levels in atoms, the Lamb shift. They tweak the electron's magnetic moment to 15 decimal places. They push metal plates together in a vacuum. The vacuum isn't sleeping. It's active. It's working. Sit with that. In the space you thought was empty, there's actually an invisible storm of particles blinking in and out of existence billions of times every second. But here's where it gets even weirder. Even if virtual particles didn't exist, the vacuum still wouldn't be empty. There's something called zero-point energy. Think of a vibrating atom, a quantum harmonic oscillator. Classically, you could stop it cold. Zero energy. But quantum mechanically? No way. Even at its lowest possible energy state, it still has energy. Specifically, Ho2. Half a quantum. That's zero-point energy. Every quantum field has it. The electromagnetic field, the electron field, the quark field. All of them. Even in the vacuum, even at absolute zero, these fields never shut down. What does that mean? They're at the absolute bottom of the energy ladder. But even that rung has energy on it. The universe doesn't allow complete stillness. There's a fundamental jitteriness woven into the fabric of space itself. So here's a question. How much zero-point energy exists? The answer mathematically is insane. You add up every field mode up to the Planck scale, and you get roughly 10^13 joules per cubic meter. That number is so absurdly massive the universe would collapse instantly. Obviously something's wrong. Something cancels most of it out. Maybe physics we haven't discovered yet. This is the cosmological constant problem one of the biggest unsolved crises in physics. But here's the key point. Vacuum energy is real, even if we don't understand how much. What does this mean practically? Take a hydrogen atom, a proton, an electron. You might imagine freezing it to absolute zero and having that electron just stop. Nope, doesn't happen. Even at the ground state, the electron is constantly moving. It has kinetic energy. That energy comes from zero-point energy. The electron can't be still because the uncertainty principle says pinning down position means momentum goes fuzzy, which means kinetic energy. Atoms are never at rest, even frozen to absolute zero. This zero-point energy isn't some quirk. It controls everything. It sets the size of atoms, keeps electrons from crashing into nuclei, holds matter together. Without it, chemistry breaks. Biology breaks. You don't exist. That quantum restlessness is foundational to reality itself. The vacuum isn't just sitting there. It's actively participating in existence. And there's even more. The vacuum isn't just fluctuations and zero-point energy. It's made of fields. Think about it. Quantum field theory, our best model of reality, says particles aren't little spheres. They're ripples in fields. An electron is a wave in the electron field. A photon is a wave in the electromagnetic field. These fields are everywhere, soaking through all of space, even in regions with zero particles. The electromagnetic field exists everywhere. At every point in space, it has two properties: electrical permittivity and magnetic permeability. Fundamental constants, epsilon naught and mu naught. They control light's speed. They determine how strongly electric and magnetic fields interact. Stop here. What does that actually mean? The vacuum has properties. It's not nothing. It's something concrete. It's a medium you can measure. And there's another field, the Higgs field. It fills the entire universe. Its background value isn't zero. It's roughly 246 giga-electron volts. Particles bump into this Higgs field, and that collision gives them mass. See the pattern? Electrons, quarks, W and Z bosons. They all have mass because the vacuum is soaked with the Higgs field. Strip away the Higgs field and particles become massless. Physics falls apart. Think about that. The vacuum isn't some empty theater where physics performs, it's the machinery itself. So what actually is the vacuum? It's the ground state of every field, the lowest energy setup. Except that ground state isn't empty. It's an ocean of quantum fields, each humming with zero-point energy, spawning virtual particles, transmitting forces. The vacuum is the bedrock. Everything else is built on it. Particles are just waves on that foundation. Forces are how those waves interact. Feynman got this at a deep level. He built quantum electrodynamics, the theory of how electrons and photons interact by swapping virtual photons through the vacuum. His famous diagrams show particles trading virtual particles. These virtual carriers come straight from the vacuum. They appear, carry the force, vanish. Without this active vacuum, forces don't happen. Electromagnetism runs on the vacuum's activity. The weak force does, the strong force too. But here's the thing. There's something profound beneath all this. The word nothing in everyday English is totally misleading. When you say, there's nothing here, you really mean, I don't see any particles. But fields are there. Zero-point energy is there. Quantum jitter is there. Virtual particles are there. The line between something and nothing completely blurs at the quantum level. The vacuum is the most turbulent form of nothing imaginable, and that has huge philosophical implications. Philosophers have been asking, why is there something instead of nothing? For thousands of years. But quantum physics flips the question. Maybe true nothingness is impossible. Maybe the most empty state allowed is still bursting with activity. Maybe true nothing can't exist in our universe. Maybe existence is inevitable because non-existence violates quantum rules. Feynman was brilliant at cutting through the noise. He'd say, don't ask why nature works this way, ask how it actually works. Observe it, measure it, calculate it. He was right. We don't know why the uncertainty principle exists. We don't know why fields permeate space. But they do. And because they do, we get the Casimir effect, the Lamb shift, zero-point energy, the entire scaffold of quantum reality. The vacuum is where it all happens, including cosmology. The Big Bang didn't start from stuff exploding into emptiness. It started with the vacuum doing what vacuums do, fluctuating wildly. Inflation, that insane early expansion, could have been driven by vacuum energy. Dark energy, which is accelerating the universe right now, might be vacuum energy. The biggest cosmology question, why is expansion speeding up, could be answered by the vacuum. We don't have it figured out yet, but the vacuum is fundamental to everything. Same story in particle physics. The Large Hadron Collider. What's actually happening when protons smash together? We're shaking the vacuum, pouring in energy to pull real particles out of the background fields. The Higgs boson was found this way. We kick the Higgs field hard enough to make it ripple to produce a particle. Without this active vacuum full of fields, there's nothing to create. High-energy experiments are really about mapping the vacuum structure. Think about what this does to your understanding of reality. You're in a room right now. Looks empty around you. Wrong. You're swimming in a turbulent sea of quantum fields. Virtual photons are blinking in and out of existence all around you. The Higgs field is handing mass to every atom in your body. Zero-point energy is keeping those atoms from flying apart. The vacuum isn't dead. It's the most basic thing in existence. And it's magnificent. Because it means reality is weirder, deeper, more interwoven than we could have guessed. Feynman said nature's creativity beats ours. He nailed it. We never would have dreamed up quantum mechanics. We'd never have imagined the vacuum just bubbling. Nature showed us the truth. Experiments, measurements, math that's absurdly accurate. And here's the mind-bending truth. Nothing doesn't exist. The most empty state possible is still something. It has structure. It has energy. It's active. The vacuum is the canvas reality paints on, except the canvas itself is thrashing, alive, fundamental. Space isn't where things occur. Space is something occurring. Stop. Process what you just learned. Those metal plates pulling together in pure vacuum. Virtual particles blinking on and off billions of times per second. The Higgs field giving mass to every atom in your body. This isn't abstract theory. This is why you exist. The nothing you thought you understood is actually the foundation of you. Feynman nailed it. Nature's imagination exceeds ours. By questioning the vacuum like he did, we learn reality is deeper, stranger, more interconnected than intuition would ever tell us. Now you know. The vacuum isn't empty, and that fullness is everything. If you want to keep questioning everything, hit subscribe. Every week I break down something fundamental that'll shatter what you thought was settled. Drop a comment. What blew your mind about the quantum vacuum? Virtual particles? Zero-point energy? Or that nothing can't actually exist? Tell me what landed with you.